Swayam Prabha. Digital India. Educated India.
Hello and welcome back. We are going to continue our discussion of optical diagnostics applied to sprays. We will look at a couple of different techniques today involving laser diagnostics. Just as a quick recap, in the previous classes we have studied basic imaging, although we did not really look at image processing. We looked at PIV, we looked at phase Doppler particle anemometry, and started to talk about other techniques. Today we are going to discuss three more techniques. One called laser interferometric droplet sizing, we will also look at laser induced fluorescence, and end with shadowgraphy. Laser interferometric droplet sizing, I will use the acronym LIDS, is known by several acronyms commercially. IPI is an acronym that is used by a company called Dantec. ILIDS is an acronym that is used by, I believe, TSI, I am not sure, and there are other companies that make this as well. The basic principle of operation is similar to a PDPA in the sense that it takes advantage of coherence. So, if I take a droplet and have a laser impinging, have a laser light source approaching the drop. If I do a very quick ray trace, this is a typical ray that is twice refracted through the drop of diameter d. There is another possibility of light reaching this observer here. So, if let us say this is me, the observer, there is another possibility by which this same light can reach this observer, which is through the mode of reflection. So, either a ray down here is reflected or it could reach the same person through the medium of refraction. A combination of these two modes of transmission of light or scattering of light through to this observer. If I focus, when the light is focused, you see a drop with two bright spots corresponding to the two predominant sources of light coming to the observer. So, this is in fact common observation, that if I see a raindrop, if you see a picture of a raindrop that is in perfect focus, you will see 2 points of bright light on either side of the raindrop. Now, if I take the same light and instead of focusing it onto a plane, so if this is my focal plane, when I create this focused image, I see this. If I take the same modes of transmission, and if I image the light say this is a focusing lens, so instead of placing the plane, the imaging plane at the focus, I place it at a slightly defocused part, what you will see at the defocused part is a set of interference fringes. So, if I draw that out, we are likely to see and all of this is the envelope of a circle, because that is what is scattering the light. So, you see bright and dark interference fringes. Okay. These interference fringes, especially the fringe width, contains information about the size of the drop, and it's really a hard signature that is coming directly from the sphericity of the drop and the size capital D of the drop. Okay. So, it is actually very rich in information, this fringe pattern. We will see how to take advantage of it a little later. So, let us see how do I practice. This is the basic principle of operation of this LIDS, laser interferometric droplet sizing. Now, how do I take advantage of this in a real system? What we do is, I have a spray nozzle, I have a spray that is formed. Let me draw this in. I take a light sheet, pass it through the spray. Now, potentially I have a lot of drops in this light sheet, of different sizes, and where the where your eye is currently, you is where the collection optics and the focusing optics are set up. So, if I now look at the scattered light coming towards me with, in fact, with in a sort of a defocused sense, every one of these drops will create a circular footprint and an interference pattern in that circular footprint. Because of this coherent light coming from two different optical path lengths, the reflected light and the refracted light takes separate optical paths, therefore, you create interference. Okay. Now, when I when I view each of these drops, I have a full circular pattern. So, if I have a light sheet of some finite thickness, which is say 1 mm, and our drops are typically much smaller than that. If I have two drops that are one slightly behind the other, they are both going to create an interference pattern, and this circular interference pattern is going to interfere in some sense spatially in the image with the interference pattern created by the drop slightly behind it. So, as a result you will see a whole set of interference fringes, but I need to identify a set of interference fringes with a particular drop in order for me to get to the drop size. The way this is done is by using only the information that is required, by only allowing the information that is required and discarding the rest. When I have a circular interference pattern, a circular footprint with interference fringes along the length of the circle, along the vertical cross section of the circle, all I care about is the fringe spacing. I do not care about the full circular footprint. So, what is typically done at the collection optics level, there is a, so I can place a slit and this is a, in some sense, a horizontal slit that looks like this. So, the vertical fringes when visualized through a horizontal slit essentially create you only see a part of the fringes that looks approximately like this. You will not see these vertical lines on top and bottom, but you will just see something like this for every drop, something like this is seen for every drop. So, if I have multiple drops, even if I have two drops that are slightly behind each other, I am able to only take a thin slice of the interference pattern created by each of the two drops, and as long as those two slices do not overlap, I have enough information to get the size of each of the two drops, even if they are close to each other spatially inside the light sheet. Okay. So, once I know this fringe spacing, and once I have information related to the position, once I know the fringe spacing and I have a bunch of these for every one of these drops, we are able to extract drop size information for every one of the drops. Now, like I said, these fringes actually, if you do the even in some sense the wave calculation, optical wave transmission calculation through a spherical drop, you will find that this fringe spacing is not exactly uniform throughout, and that contains information that is specific to that drop. So, in terms of sphericity, for example, or some kind of a difference in the refractive index of the drop. Now, so I am able to relate every drop, and by knowing, let us say, the midpoint of this pattern, I am able to determine the size and its position uniquely. So, if I use LIDS, which is laser interferometric droplet sizing, along with double pulse photography, where I take two pulses and get two images slightly apart in time, because I am able to uniquely identify every drop in this image we can calculate the velocity vector of every one of the drops. So, essentially an extension of this So, first of all LIDS is based on relating the fringe spacing to size. Now, if I combine LIDS plus double pulse imaging, you can get LIDS plus particle tracking velocimetry which allows us to measure the velocity of every particle in the spray. We have looked at several different techniques for both particle sizing or drop sizing and velocimetry. Let us quickly see the advantages and disadvantages of the various techniques. First of all, so let us list for each one of the various techniques the advantages and disadvantages, but before we do that maybe we should look at one more technique called shadowgraphy. This is similar to the one we used before. It is actually in some sense the simplest of all imaging techniques. You potentially have a very bright light source passing through a diffuser, and on the other side is your camera. Typically this has to be a high speed camera in order to be able to image the spray. The basic principle of operation, when I am looking at a bright light directly in front of me, I am going to see the shadow of any object that is between me and the light, and so the camera sees shadows of these drops. So, you might see drops that are back here as well as drops that are in front, all cast a shadow on the image, but I could have a specific plane on which I focus the camera and only look at the shadows in that focused plane and discard the images on either side. So, essentially this is the clarity of the image depends on the depth of focus. The smaller the depth of focus, the higher the clarity, but smaller the depth of focus, the less chance I have of capturing a sufficiently large number of these drops in any one image. So, they are contrasting requirements of this system. Once I have an image, ideally I would like an image with like dark shadows that are circular, or they do not have to be circular, but let us say they are of some very clearly defined shape. In reality what you will end up seeing is one of two things. You will see a little bit of a blur where the drop is maybe dragged through a certain distance. This is because in spite of using the highest speed camera, the exposure time on some of the high speed cameras may be still long to get a crisp frozen image of the drops. Okay, so, the solution to that very often used is to have, instead of a bright light diffuser, there are fluorescent emitters, emitter plates if you will, that are excited by a laser pulse. So, this would be a substitute to the bright light source. The advantage of this light source is that you have first of all a laser light source that is impinging on a fluorescent on an absorbing medium, a medium that absorbs that wavelength and emits a slightly longer wavelength, but the emitted intensity is relatively uniform and is only controlled by the concentration of the fluorescing agent. In reality, of course, even that intensity is not important. The fact that that emission occurs over a very short period of time is what is important. So, the fluorescence lifetime of these agents is very short, typically much shorter than the exposure times on your high speed cameras. So, if you can synchronize the high speed camera to the initiation of the fluorescing time or the pulse initiation time, one could capture a very crisp image of the drop. The biggest advantage of shadowgraphy is that I am able to capture sizes of drops that are known to be aspherical. If you look at the previous techniques, whether it is phase Doppler particle analyzer or LIDS, they all assume sphericity in order to get to the size. So, this is a technique, since you are directly visualizing the blobs of liquid in motion, frozen however, you do get you are able to see images of drops that are not spherical, and by appropriate image processing get shapes of like you are able to characterize the shape of the drop apart from just the size. So, if I now look at an image coming from the fluorescing agent, I am able to see drops like that are spherical, but I may also have a second drop that is slightly behind the first drop, and in my image I may create a shape that looks like this. Okay, and both these drops may still be within the depth of focus of what I need, of my imaging optics. So, I can with my naked eye see that there are two separate drops, and I can use appropriate image analysis techniques. So, start with edge detection and look at sudden change in the gradients of the edge, and from there identify this composite image of two drops one behind the other as actually being two separate drops, and you can ascribe a size to each of the two drops. Now, if I have a ligament of sort, say typically like if I am now very near the nozzle, I may actually see a drop that looks like this. I can use this technique to not only get the size of that drop in the plane of the image, but also get some feel for what sort of non-equilibrium shapes are existing in the near nozzle region. So, this is a slightly more versatile technique in the sense that you are able to image drops that are not spherical. One of the biggest disadvantages of this technique is that you really still cannot go very close to the nozzle. In spite of talking about non-spherical drops, because once your droplet number density becomes large, a classic case is a diesel spray. It is very difficult to image the near nozzle region in a diesel spray to get to some kind of indicators of what sort of drop sizes may exist in that part of this in that part of the in the near nozzle region of the spray. Now, we did not talk about another technique. In fact, one of the oldest techniques for particle sizing is what is called diffraction particle sizing. The pioneer in this field is called was a company called Malvern, which was in fact it preceded all other forms of optical diagnostics for space except photography. Now, the basic principle here is that I have a laser source that puts out a light beam. The light beam shines through a spray, and all the little drops that are in the light beam are scattering light. So, essentially by the medium of diffraction, by the mode of diffraction. So, every drop, again assuming sphericity, creates what is called an airy pattern of diffraction. So, I am going to exaggerate this part just to make the point. If I take this particular drop, it creates a pattern where the light intensity versus radius takes on a pattern that looks like this. So, you see a very bright spot in the middle, one more bright spot a certain angular deviation away, and a third bright spot. So, you see these clear peaks. This is called the airy diffraction pattern. From a spherical drop, and this airy diffraction pattern has these clear peaks, and these peaks are directly related to the drop size. So, the way, remember, this creates the diffraction creates an angular diverging pattern. So, with again some appropriate imaging optics. So, it is quite usually it is just a single lens is enough, and the detectors are semicircular arrays. So, I mean the airy diffraction pattern for a circular drop in a laser beam is